Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dr. Junior, your math tutor, and I am an instructor of mathematics at the University of Liberia. In today's lesson, we want to continue from where we stopped in the previous lesson, that is finding derivatives of trigonometric inverse functions using the trigonometric substitution. So in the previous lessons, we solved a lot of problems using the trig substitution. So we want to look at the last problem now under this topic, that is derivatives of trigonometric inverse function using the trig substitution method. So the question says y equals to tangent inverse of the square root of 1 plus x squared plus x. So like we said in previous lessons, our objective is to ensure that whatever is within this angle, whatever expression that we have right here, should just be equal to a trig function. Now, if this is tangent, now our goal should be that we make this expression to be tangent. If this is sine, our goal should be we make this to be sine as well, so that we bring in the trig inverse, a property that states that tangent inverse of tangent of x is just equal to x. So for this case, now we say let x equals to tangent of x. Now let's use another angle, theta. Now if we solve for this theta, we can now take theta on both sides of a tangent on both sides of the equation. So tangent inverse of x is equal to tangent inverse of tangent of theta. So tangent inverse of x is equals, now tangent inverse of tangent of theta is just equal to theta. So we know that x is equal to tangent of theta and theta is equal to tangent inverse of x. Now we are going to use these two equations later. So let's keep them. Now we go back, we have y equals to tangent inverse of the square root of 1 plus, now x is tangent of theta, but it is squared, so we say tangent square of theta, plus x is tangent of theta. The next step is that we know that there is a Pythagorean identity that states that the square root of 1 plus tangent square theta is equals to secant of theta. So y equals tangent square theta, tangent inverse of this whole thing now is just secant of theta plus tangent of theta. But remember that our objective is to ensure that whatever expression that is within there should just be tangent of theta or tangent of an angle. So we can rewrite these expressions in terms of sine and cosine. So we have tangent inverse of 1 over cos plus sine of theta or over cos of theta. So this is the reciprocal identity for secant, and this is the quotient identity for tangent. Now we can find the LCD. So we know that the LCD for the two is just cos of theta, and then the numerator will just be 1 plus sine of theta. So we can bring in some identity for these expressions so that we'll be able to solve this problem. So what are those identities that we can bring in? We can bring in the half angle identity for sine and cosine, and also bring in the identity for 1. So we know that sine of 2 theta is equal to 2 sine of theta cos of theta. So if we divide every angle by 2, it means sine of theta will be 2 sine of theta over 2 cos of theta over 2. Also, cos of theta, we know that cos of 2 theta is equal to cos squared theta minus sine squared theta. So if we divide every angle by 2, it means we will have cos of theta to be cos squared theta over 2 minus sine squared theta over 2. Lastly, we know that the Pythagorean identity cos square theta over 2 plus sine square theta over 2 is just equal to 1. So wherever we see this 1, we should replace it with this identity. So now we have y equals to tangent inverse of, so this was 1 plus sine of theta all over cos of theta. So what is 1? 1 is now cos squared theta plus sine squared theta. And then sine of theta is just 2 sine of theta over 2 cos of theta over 2. All divided by cos of theta. Cos of theta is cos squared theta over 2 minus sine squared theta over 2. Now, to factorize this expression, because you see that we can easily factorize this. To factorize this expression, you can just think of rewriting these trigonometric function in terms of algebraic expression. Now, you are not, this is not a long process that you're going to do in terms of maintaining those algebraic expressions for a long time. No, you just want to sense the kind of factorization that you want to do within this problem. So we know that cos square theta. So if we say cos of theta to be equal to x and sine of theta, say theta over 2 now, right? So this is theta over 2, theta over 2. So if theta over 2 is equal to x, this is also equals to y. You see that you have x squared plus y squared plus 2xy. So if you rewrite this, you can have it like x squared plus 2xy plus y squared. Now to factorize this into product of two binomials, we have x times x give us x squared. Then y times y will give us y squared, right? Now let's multiply. You have positive, so we'll plus here, plus here. Now let's prove it. So x times x is x squared, x times y is xy, y times x is xy, y times y is y squared. So the middle term here is just 2xy. So we have the 2xy, right? So this is how we're going to factorize this expression. X plus y, x plus y. So x plus y is being multiplied twice. So it's going to be x plus y all squared. Now, let's do the one down. So this is x plus y all squared, right? In the numerator. What's about the denominator? So this is also x squared minus y squared. So this is difference of two squares. Therefore, we can have x minus y and x plus y. So you see, now let's put it in. So we have y equals to tangent inverse of. So this is now x plus y times x plus y, right? But we know that our x is cos of theta over 2 and our y is sine of theta over 2. So we're just going to say cos of theta over 2 plus sine of theta over 2 times cos of theta over 2 plus sine of theta over 2. So if you multiply these two, it will give you the numerator. Divide, difference of two squares. So we have cos of theta over 2 minus cos of theta over 2, sine of theta over 2 times cos of theta over 2 plus sine of theta over 2. So what do you observe? This, we cancel one of it. So what are we left with? We're left with y equals to tangent inverse of cos of theta over 2 plus sine of theta over 2 all over cos of theta over 2 minus sine of theta over 2. Now, if we look at this expression looks similar to the identity tangent of x plus y, or we say a plus b, equals to tangent of a plus tangent of b all over 1 minus tangent of a times tangent of b. So this looks similar to this expression. So what we need to do is, since we want to write it in terms of tangent, we can divide every term by cos. Because if we divide every term by cos, you divide it. Why are we dividing every term by cos in the first place? Because we know that tangent is equal to sine of theta over cos of theta. So since we want tangent, we can divide every term by cos, both in the numerator and the denominator. Or we say we rationalize cos of theta. So we have y equals to tangent inverse of, so let's do it, cos of theta over 2 or over cos of theta over 2 plus sine of theta over 2 or over cos of theta over 2 divide cos of theta over 2 cos of theta over 2 sine of theta over 2 cos of theta over 2. So now we have y equals to tangent inverse of, this is 1 plus, this is tangent of theta over 2, and then this is 1 minus, this is tangent of theta over 2. So you see, we sense that this identity, this expression that we have was similar to this particular identity, which is the tangent of a sum. But there's something that is missing. Something is missing. In the first term, we have 1. In the first term here, we have tangent of a, which means that the first term is also tangent function, right? So in order to make this to be tangent, as well, right, we can rewrite this one. Now we know that from the 45 degrees right triangle, the legs are equal, and the length of the hypotenuse is the square root of 2. Now this 45 degree, if you convert 45 to radian measure times pi over 180, it means 45 into h 1 times 45 into 180 4 times. So 45 degree is pi by 2 or pi by 4. Now tangent of pi by 4 is just opposite over adjacent, which is 1. So it means this 1 can be rewritten as tangent of pi by 4. So now we have tangent inverse of y equals, the first one is tangent of pi by 4 plus tangent of theta over 2 divide 1. Now we are not going to rewrite this 1 because here is 1. Minus, the first one is tangent of pi by 4 tangent of theta over 2. So we clearly see that this entire expression here is just equal to tangent of a plus b. A plus b. What is our a? Our a is pi by 4, and our b is theta over 2. So y equals to tangent inverse of pi by 4 tangent of pi by 4 plus theta over 2. So tangent inverse of tangent of an angle is just equal to that particular angle, pi by 4 plus theta over 2. So we're almost done. We're almost done. So now we need to find the derivative, but we need to bring in theta. Initially, we solve for theta. So we have y equals to pi by 4 plus theta now is tangent inverse of x. Now this is 2. So let's find the derivative now. So y prime now, or we can say dy by dx, if we wish to, is just equals to the derivative of a constant goes to 0. The derivative of, now we can just factor out this 2. The derivative of tangent inverse of x is just 1 all over 1 plus x squared, right? So dy by dx would just be equal to 1 all over 2, 1 plus s squared. So this is our final answer. So this is how we find the derivative of trigonometric inverse functions using trigonometric substitution method. So thanks ever so much for watching, and see you in our next lecture. Thank you.